Hey there everyone, welcome to your second lesson on further maths, algebra. So today is going to be a little bit of a mix and match of all sorts of things. Just general advanced algebraic techniques that you need to be aware of, and we're going to need for certain things that are part of the further maths syllabus. So um, here, so first of all, we'll look at expanding brackets. We're basically going to extend this idea to uh, three or potentially even more brackets. Factorization. How do we deal with factorization with potentially higher order terms? Greater than say a quadratic. It could be powers of three or more. Indices and roots. We're going to be building upon that. So that's all to do with powers and roots, not necessarily just square roots, but other roots as well. We're going to look at rational expressions, which are basically when we have like one like polynomial divided by another polynomial, um, and we'll learn how to apply what we know about fractions um, to these rational expressions. And then we're going to be looking at functions. We're going to look at piecewise functions, which are, functions that are defined in multiple parts. And then we look at domain and range, which is our key concepts of functions as well, to sort of see what range of x values and y values that a function is valid for. Because sometimes it's not valid for all values. And that's something we need to be able to analyze. So, first of all, expanding brackets. So, how would we deal with a situation like this? I'm assuming you're already very familiar with single brackets, double brackets. How do we expand those? We want to instead expand three brackets. And it works in very much the same way, where you're basically taking if we look at the leftmost bracket, and we're taking that and expanding it through every other term in all the other brackets. So you imagine taking that term and multiplying it by the 5x and then the x, and then you could multiply it by the 5x and the minus 5. Then you can multiply it by the 1 and the x, and then you could multiply it by the 1 and the minus 5. And then you'd have to do the same thing again with the minus 3. That's quite a long and messy way of doing it, and you could potentially miss a term or make a mistake. So what we'd often recommend doing is something like this, where you just focus on the first two brackets first. And you can expand this out in the way that you're already familiar with, expanding double brackets, and then, collect together your like terms. So you might have noticed here, yes, this is going to produce a quadratic. And then what we do is we take that quadratic and multiply it by the remaining bracket that we haven't considered yet, the x minus 5. And then multiply that out. So we've got to take each term of the quadratic and multiply it by the x, and then do it again for the minus 5. And you should get this. And again, we just have to collect together like terms, and you see what we produce here is a cubic equation. We're going to be looking a lot more at cubic equations in a later lesson. So that's it really for expanding brackets. And you can imagine extending this to 4 or 5 even if you needed to, where you just look at 2 at a time. Expand 2 and then bring the next one in and now expand that, and then bring the next one in and expand that. You could quite easily do it that way. So we're taking what we already know and we're just extending it to more brackets. So next, factorization. So there's just sometimes there is no way of factorizing simply. Like say if you take an expression like this, a lot of the times you would have to expand all of this out and then you'd have to factorize it from there. But sometimes if the factors line up well, we can find shortcuts, and we need to spot those shortcuts because it can save us a lot of time. And here you might want to look here, like pause for a second and have a look at this and see if you can notice what we could factorize here without having to expand this out. So hopefully you've spotted what that is. If you haven't, notice that both of them have a factor of x plus 4. You see the first one is x plus 4 to the power 4. The second one has an x plus 4 to the power 3. So what we could do is we could take that x plus 4 to the power 3 out. And you see in the first term, what's going to be left over is just an x plus 4. In the second term, it's going to be 2x minus 3. So that's what gets left inside the first bracket. So yeah, take a look at that and make sure that makes sense to you, what we've done there. We've taken out a factor of x plus 4 to the power 3 from both terms. And then in that first bracket, we can just bring together like terms and we essentially get 3x plus 1. And you see, we've managed to fully factorize that without having to expand all this out. Because if we did expand all this out, you might be able to notice that what we're going to get is what's known as a quartic polynomial. You're basically going to get an x to the power 4 term. And something like that would be very difficult to factorize. So we wouldn't want to have to go down that road. So yeah, noticing these shortcuts like this is really, really important. If you've got an expression like this with like these high powers, this is the only way you would be expected to factorize it. You wouldn't be expected to expand it all out because, like I said, that's just it'd be too much. So indices and roots. Let's move on to this. So first of all, your laws, indice laws, you should already be very familiar with many of these and why they work. Um, so if you're not, I have lessons in the regular GCSE syllabus that cover this in a lot more detail. How these laws work and specifically why they work. So what we do is look at just a couple of examples, like more advanced examples of using this. Because the more basic examples you should already be familiar with from just regular GCSE syllabus. So say if we take something like this and we're trying to simplify this expression, how would we do this? So we need to use our indice laws. So we need to think which indice laws can we apply here? So you look on the numerator, there's not really much we can do there. X cubed plus x to the 4. There's no way of combining those. But on the bottom, we've got x squared times x to the minus 5. And we've seen the first indice law tells us how to multiply two terms like that, where we've got x to the power one thing times x to the power of something else. You see those powers will end up adding together. And so we get 2 plus minus 5, which becomes minus 3. Great. So now we're dividing by minus 3. We're dividing by x to the power minus 3. How can we now simplify this further? Well, there's multiple ways you could do this. If you don't like that term being on the bottom, you could bring it up to the top, because looking at our fourth indice law there, you see that a to the power minus m is the same thing as 1 divided by a to the m. Similarly here, x to the divided by x to the minus 3 is like dividing by x to the power 3 twice. It's like doing divide. And what you find is that essentially cancels out and it becomes a product like this. In a similar way, how when you do a minus minus, it becomes a positive. So say if I did 5 minus minus 2, it becomes 5 plus 2. It's kind of like the same idea here. So that negative power is like we're doing divide by x to the power 3. So we're doing divide. It becomes product, like multiplication. And then this becomes quite easy to expand out, by adding the powers, we get x to the 6 plus x to the 7. So that's how I would approach something like that. Similarly, at that second step, what we could have done is just straight away divided by x to the minus 3. Like if we look at our second indice law, we could have done x to the 3 divided by x to the minus 3, and that would become x to the power of 3 minus minus 3, so that would become x to the 6. The second term would be x to the power 4 minus minus 3, which would become x to the 7. So you could have got it that way as well. But yeah, that's how we'll do that one. Let's take another example here. So another complicated example with quite a bit going on. And how could we perhaps, simplify something like this? And we want to just put it as a power. So we could do something like this. First of all, a root is basically the same thing as a power of 1 over that root. So a third root is basically the same thing as taken to the power of 1 over 3. And that's where they then combine together to become this. So you can see in that last indice law, You see how the roots and powers combine together to produce a fractional power like this. Um, and then we could use as the fourth indice law there to turn this fraction into just like a simple like number times x to some power. So like this. So we see divided by x to the power 2 over 3 is the same thing as times it by x to the power negative 2 over 3. So this is a common thing you'd be asked as well, where you want to, convert it from one form into another. You'll see a little bit more of this when we look at differentiation in a much later lesson. You see that first expression of 3 over the cube root of x squared. By converting it into this form of 3x to the power minus 2 over 3, you'll see this is much easier to work with. So this is that would be one example of where you would use something like this. So yeah, we need to be comfortable with these indice laws and roots and how they combine together at a more advanced level for further maths. So one other thing you could get asked about, which is not part of the regular GCSE syllabus, would be ordering numbers. Numbers when you don't even know what they are. So say we've got a series of x to different powers, integer powers, and we're told that x lies in this range between -1 and 0. And we want to use this information to put these in order. So you've probably seen these kind of ordering questions before when dealing with proportions, like put fractions and decimals in order. So how would we do it here? So you might want to pause here and give this a go for yourself. Like think about it. Like how does that range of x values, how would that affect respond to various powers? So yeah, if you want to give that a go yourself first, yeah, give a pause here and try that. Otherwise, let me take you through what you would do here. So first of all, you want to consider the values of x that you have, because how different numbers respond to powers in different ways, don't they? So these are the things we've got to consider here. What we've got is we've got an x that is negative, and we've got one that's a fraction. So note that when you've got a number that is a fraction, like say if you had a half, for example, if I do half to the power of 2 or 3 or 4, notice the number gets smaller, doesn't it? Because I'm doing a half times a half times a half. It's getting smaller. Whereas if you do a number greater than 1, like say 2, and I do 2 to the power of 2, 3, 4, whatever, you see the number's going to get bigger. It will go 2, 4, 8, 16, so on. So that's something to be mindful of. Between 0 and 1, a number will get smaller when you're taken to powers. And when it's greater than 1, it's going to get bigger. Another thing to deal with is the fact that it's negative. So when you take to an odd power, it will remain negative. But if it goes to an even power, it will become positive. So we've seen this like with squaring. When you square a number, it remains positive. But if you went to the power 4 to the power 6, say, as well, it would also become positive. But if you do a negative number to the power of 1, 3, 5, it will remain negative. And you might want to try that out yourself for, some example number, like say if you do -5. If you keep times it by -5 over and over and over again, you'll notice the sign keeps flipping. It goes positive, negative, positive, negative. So yeah, those are the two things we need to be mindful of here. So if we now start assessing these different powers, well, x squared we can see is going to be between 0 and 1, because but it's going to be smaller than x, isn't it? Because if we're squaring this number that's a fraction, it's going to become smaller in terms of its absolute value, but it's also going to become positive because we're squaring it. So we can see x squared is going to lie in this range. We can see x cubed will lie in this range as well. Basically the same range that x is in, but it will be closer to 0 because it's still a fractional value. And remember, squaring a fraction will reduce its absolute value. It's going to move it closer to 0. When I say absolute value, I'm basically referring to the value of the number when we don't worry about the sign. So if the absolute value is getting smaller, it means it's just moving closer to 0. Next one, x to the power 0. Nice, easy one. It's always going to be 1. Doesn't matter what the value of x is unless it was equal to 0, but it can't be in this case. So yeah, it's always going to be 1. X to the negative 1 is going to be less than -1, isn't it? So what we're basically doing here is the reciprocal of the number. So say if x was equal to -1/2, for example, that lies in that range. If we did that to the power -1, remember -1 means to take the reciprocal. You flip that fraction upside down, it becomes -2/1, which is -2. So you see it becomes less than -1. So yeah, if you've got a fraction, like in the same way how like a number greater than 1, if you take the reciprocal of it, it goes between 0 and 1. It essentially becomes a proper fraction. It works the same in reverse. If you take a proper fraction, a number between essentially 0 and 1, or 0 and -1 in this case, and you do the reciprocal, it's going to end up becoming greater than 1 or less than -1, as the case may be, because it's negative here. And finally, this one, it's going to be the same thing because you're flipping upside down. Its absolute value is going to be greater than 1, but it's going to be positive this time because what you're doing is you're essentially flipping it and then squaring it. And now we've kind of got all the information we need to start putting these in order. So you can see, first of all, that the smallest one is going to clearly be x to the -1 because it's less than -1. Then the next one, the next range to consider is ones between -1 and 0. And you can see there are two numbers, x cubed and the x are both between -1 and 0. But remember, like I said, x cubed will be closer in absolute value to 0, won't it? Because it's a fraction and you're cubing it. It will move closer to 0. And because it's negative, closer to 0 means you're making it bigger. So x is going to be the next biggest one, and then x cubed. X cubed will be bigger than the x. So that's the only one where it requires a little bit more thought because they're both lying on the same range. But now it becomes a lot easier because we've got x squared is going to be the next one because that's in between 0 and 1. Then the next biggest one is going to be x to the 0 because that's equal to exactly 1. And then x to the -2 is going to be the biggest one because it's greater than 1. And so you see there, for any value of x in that range, we can determine it's going to be this order, regardless of what that x value is. So there you go. So those are some pivotal points where numbers, how they respond to powers and roots will change. Is basically at plus or -1 and at 0. Whenever you cross any of those boundaries, the way the number responds to a power is going to change. So that's something to be mindful of there. So basically, yeah, is it a fraction and is it a negative? That those things will affect how it responds to power. So yeah, quite a tricky problem, that one. But I hope that makes sense and you was able to follow that. Right, so let's move on to rational expressions. Still got a couple of topics left to cover. So, rational expressions. So this should be something that is still quite familiar to you if you've already covered the standard GCSE syllabus. So it's basically we want to look at arithmetic with algebraic fractions, otherwise known as rational expressions. How do we do this? Well, we just need to extend our understanding of fractions to the algebra form. So when you're adding fractions like this, remember you need to get those denominators the same first. So what I would do is I would take that first fraction, the 5 over x plus 1, and I'll times the top and bottom by x plus 2. And I'll take the second one, and I'll times the top and bottom by x plus 1. And now notice both of those fractions would have x plus 1 times x plus 2 as their denominator. In which case I can now put them together to become this. So notice there, yeah, you've got 5 times x plus 2 over that denominator plus 2 times x plus 1 over that same denominator. We can basically put them together into one fraction like this. So that's the key there. If we want to take two fractions and put them together as one, you need those denominators to be the same. It's the same concept as when you're dealing with just regular numbers, but here we're doing it with algebra instead. And we can always then expand and simplify the top, the numerator to get 7x plus 12, and then perhaps factorize even if there was the possibility to do so, but there is no, we can't factorize that, so we just leave it as is. The denominator we could just leave factorized because that's quite useful to have it in that factorized form. Now, when it comes to multiplying two fractions, or algebraic fractions like this, is even easier. One thing to note as well, if I was to subtract those two fractions, it'll work in very much the same way. You need to make the denominators the same, but you're just going to be subtracting now instead of adding. Multiplying like this is actually easier because we can just simply multiply across the top and multiply across the bottom, and we get this. And there you go. That's all we need to do. So yeah, multiplication is quite simple. Division is also quite simple, but we need to do one that will check first. So when you're timesing by a fraction, what you're essentially doing is you're timesing by the top and you're dividing by the bottom. If you then divide by that fraction, what you're doing is you're essentially flipping that dynamic. You're now going to be multiplying by the denominator and dividing by the top. So what you're essentially doing is you're multiplying by the reciprocal of that fraction. So it will look something like this. So rather than dividing by 2 over x plus 2, I am going to multiply by x plus 2 over 2. So, well, we've already seen how we can do that quite nicely. Multiply across top, multiply across the bottom, and we're done. And we could always leave it in this factorized form because that could be quite useful. So there you go. That's first things first. You should already be quite familiar with that, but there's a little recap of how we do arithmetic with algebraic fractions. Let's consider some scenarios like this. How would we solve an equation like this? So there's more than one way we could solve this. First things first, you might be thinking is we just multiply out that denominator, which is quite often a technique we'll use with algebraic fractions. If there's a division going on there and we don't like it, well, multiply by that denominator, and it'll disappear. And you see it appears on the other side, multiplying the two. And we can expand it out, move everything to one side. You see what we're going to get here is essentially a quadratic. So yeah, when we clean this up, collecting together like terms and all that, you basically get a quadratic. Solve this in the way you normally would. This can actually be factorized to get this, and then we can solve to get x equals 4 and x equals 22. So I'm assuming you're already very familiar with quadratics, how to solve them, factorization, quadratic formula you can see at the bottom of the screen there, or you could even perhaps use completing the square. Solve it in the way that you prefer. However, let's take something like this. Rather than having this algebraic fraction equal to 2, maybe it's equal to a little expression of x, like x minus 2. Now we can't solve this in the same way, because if we times out the denominator, on that right-hand side, we're going to end up getting a cubic equation. And we haven't looked at how to, we can solve that, but not always, and it can be a lot trickier, and we're making a lot more work for ourselves. Ideally, we don't want to do that. So what we want to do is essentially get rid of a factor if possible. Now, this is not something you can always do, but this is a common thing that you'll be tested on. Whenever you got a fraction like this, where there's quadratics involved on the numerator and denominator, or one or the other, you want to look for common factors. So if we want to find common factors, we need to factorize. So if we factorize the top and bottom and see, is there a common factor? And in this case, you can see, yes, there is. There's a common factor of x minus 4. And so we can cancel that out. And now we can solve this in the same way we did before, where we multiply out the denominator. And you see, we're not going to get like a cubic or a quartic polynomial or anything like that. We're just going to get a nice quadratic again, like this. So you expand out, multiply by the x minus 8, expand out the brackets, bring everything to one side, collect like terms. So all these algebra techniques that you should already be very familiar with, you'll find you'll get a quadratic like this. Now we need to just solve that quadratic, and you'll find you'll get the values of x equals 1 and x equals 10. So that's what we do in that scenario. So don't be too keen to just multiply out that denominator, even though that is the way we have to solve algebraic fractions. But sometimes you want a little work with it first, try and find common factors and get rid of those first before you multiply out. Otherwise, you might make a lot more work for yourself. So there we go. So now let's look at functions. The last thing we need to look at, first of all, piecewise functions. So what do I mean by a piecewise function? It looks something like this. And this might look a bit daunting at first, but it's actually not too bad. What we're doing is we're basically saying that this function f of x, it's going to follow the line. It's going to be basically equal to 4x for all x values less than 0. Then when x is equal to 0 to 8, it's going to equal this other expression of x squared minus 8x. And then for x greater than 8, you're then going to follow this expression 16 minus 2x. So hence why it's called piecewise. You're defining a function in various pieces with various ranges of x, and you can then use everything you already know about graphs and functions and all that. You've just got to make sure you apply it to the right piece. So let's try, plotting this. So say if I plot the four functions, so y equals 4x will look something like this. Y equals x squared minus 8x will look like this. And y equals 16 minus 2x looks like this. And you can see they nicely line up at the boundaries. So you'll only ever get asked questions like this where they line up at the boundaries. So say when x equals 4. So you see that there's a boundary. As we go from one piece to the next, it does so at x equals 0, and it does so again at x equals 8, doesn't it? And we can see at x equals 0, you find it's equal to 0, regardless of whether or not we put it into 4x or x squared minus 8x. And at the other boundary, at 8, when we put in x equals 8 into x squared minus 8x, or into 16 minus 2x, again, it also comes out to 0. It doesn't always have to come out to 0, it just has to come out to the same value. So you see they line up nicely. And we can put that on the graph there. So you see 0 is at the origin, 8 is at that point where the blue and the green cross. And if we now want to just show this piecewise function explicitly, it's going to look like this. So you see how it follows that 4x line up to 0, then it does the quadratic up until 8, and then it goes back to 16 minus 2x, another linear function again for x greater than 8. So this is what that piecewise function would look like. So a bit of a funny function here. Like I said, you'll only ever get examples like this where they do line up nicely, but you'll see how it kind of becomes pointy in places. This allows us to define now more advanced functions, more complicated functions that maybe don't always act like a quadratic. Maybe it acts like a linear part of the time and then quadratic the other time, or so on. So how do we work with these? Like, say if we wanted to find out what f of 5 is, how would we work out what f of 5 is? Well, we need to identify the correct piece. So f of 5, so x equals 5. Where does x equal 5 occur? So you might be able to see that's going to be the middle piece, isn't it? So x squared minus 8x. So if we put in 5 into that one, that will give us the output of our function, minus 15. So just as usual, if we want to put in a particular input, we just need to apply it to our function and calculate the output. You just need to make sure you select the right piece of the function. Similarly, we say f of 20. So x equals 20 now. What piece would we have to apply here? Well, it's going to be the third piece because it's greater than 8. So we put 20 into 16 minus 2x, and you find you get minus 24. So that's relatively straightforward to begin with. How do we do it in reverse? Like say if we're trying to find the input for a given output of the function. So f of x equals minus 12. How do we find what values of x correspond to minus 12? Now here, what you might find is you're going to get a lot more values of x. So say if y equals minus 12. So that y represents our outputs, doesn't it? So we're trying to find where does y equals minus 12. You can see that intersects the graph at multiple points. Actually, 4 points in total. You can see 3 points on that graph, but you see that third part of the function as it's going down, that would eventually hit that line as well, wouldn't it? So there'd actually be 4 solutions here. And how we can find those 4 solutions? Well, we basically need to solve where um, each of these pieces equal to minus 12. And so you can see for the first one, it's going to essentially be minus 3. And we could just solve each of the other ones in the usual ways we would. So you see the second one's going to be a quadratic problem. The second one, the third one, sorry, is going to be just another linear problem we need to rearrange to solve for x. If you can't solve the equation, if it just kind of evaluates to nonsense, then that signifies that it doesn't intersect that part of the function. So, or it might do, but you need to be careful that the values you get are within the appropriate ranges. So for the first function, we get x equals minus 3. Well, that's less than 0, so that's okay. The second function, we get the values of 2 and 6. Well, they're both between 0 and 8, so that's okay. And the final one, we get x has to be greater than 8. Well, 14 is greater than 8, so it's all okay. So these are all perfectly valid solutions. So yeah, you need to check that because they might not always be valid. So there we go. That's how we would deal with that. And let's look at something finally. Domain and range. I've already kind of spoke about these a little bit, but now we're kind of attaching a proper word to it with a definition. So domain and range. Like say if we have a function like this, a simple little function, 3 minus x. But say we don't want 3 minus x over all values of x. We just want it between this range. This range of x values. Well, this is what we refer to as the domain of the function. It's basically what range of x values are we looking at. And then from that, we could draw a graph. And you notice this graph, it doesn't continue on across the whole axes. It's just going to go between these 2 points. Because you see between x equals minus 3 and x equals 2. And you could always calculate the corresponding y values there are going to be 6 and 1. And so you see it's just going to go between those 2 points. Similarly, we could find what's called the range of the function, which would be this, which is basically the range of y values. Sometimes it's referred to as codomain. You probably won't really see that word being used much, but just in case you do, sometimes it's called codomain for the y values. And you can see in this case, yeah, it goes between 1 and 6. So let's look at another example, like a piecewise function again, and we want to consider domain and range. And if I plot this, you might want to pause in and try plotting this yourself, using what you now know. Otherwise, if I plot it, it will look something like this. So you see it's doing minus x from minus 4 to 0, and then it will do x squared from 0 to 2, and then it will start going down again, 10 minus 3x for x equals 2 to 4. And we can calculate those points. You see, we've got this point here at the start. You got this point here, where it goes from x squared to 10 minus 3x. You can see at x equals 0, it's just at the origin, isn't it? And then we find the final point is all the way down here. So now we want to see what the domain is. So we've got the domains for each piece of the function. So the first piece is minus 4 to 0. The next one's 0 to 2. The next one's 2 to 4. And note as well the inequality signs. You notice how there's not overlap. So you see the first one is strictly less than 0, but then the next one is greater than or equal to 0. So you see there's no overlap there. If they were both, sort of less than, like say if the first one was less than or equal to 0, then it'd be confusing at the point 0, wouldn't it? Because you don't know which function it'd be using. So that's another thing to be mindful of as well, that there isn't overlap. But yeah, we've got those domains for each individual piece. The overall function, well, it's going to be this, isn't it? You see it's going from minus 4 to 4 in the x direction. The range, we can see the range goes from -2 to 4. You see the highest y value is 4, the lowest y value is -2. So that'd be the range. So there we go. Relatively simple concept. The domain is just a range of x values that the function goes over. The range is the number of like the values of y that the function goes over. And that's it. So let's leave that there. So we've got another challenge question for you here. So let's take a look at this particular problem I'm about to present you, and we want to find the range, and I'm going to show you the solution, and I want you to try and find out what is wrong with my solution. So say if I have this function here, like a relatively simple function, just a nice quadratic, and we're looking here on the domain of 0 to 3, x equals 0 to 3. So, okay, what I do, I put in x equals 0 and x equals 3, and you see I get these two values. Y is going to be 10, y is going to be 1 at these two values. And so therefore, I conclude that the range is between 1 and 10. Now, there's nothing wrong with my calculations here. Like, I haven't made an incorrect calculation or anything like that. But this answer is wrong. The range is not 1 to 10. And I want you to think, why? Why is that wrong? Maybe you can visualize it in your head, like thinking about how the shape of a quadratic graph. Or maybe you want to actually sketch this out or even draw it. And you should be able to spot what the true range is perhaps going to be. Or at the very least, you'll be able to see it's not going to be this. So there's a little challenge question for you there to test all of your understanding of range. And certain things you'd have to be careful of when trying to calculate the range. So there we go. Let's leave that there. Here's your takeaways for today's lesson. Make sure you check all those things on the right that those are things you know how to do. I've got a tip for you there. Next time we're going to be looking at something known as the binomial theorem, which is a technique that allows us to expand out potentially many brackets. We could have like maybe 10, 15 brackets even, under certain circumstances though. So I'll see you there next time for that work on binomial theorem.